In this video tutorial, we will learn greatest common divisor, or GCD. Assume we have numbers a, b, c, and so on, l. And if we have an integer that divides each of these numbers, this integer is called common divisor of these numbers. The greatest of these divisors is called greatest common divisor, and shortly called GCD. Greatest common divisor of our numbers is denoted as this. So this is greatest common divisor of numbers a, b, c, and so on, l. If greatest common divisor of these numbers is equal to 1, if we have this, in this case, these numbers are called relatively prime. We also have to be relatively prime in pairs. Means that every two numbers in the set is relatively prime. For example, these two numbers are relatively prime, these two numbers are relatively prime, and every two numbers in the set is relatively prime. In this case, we call these numbers relatively prime in pairs. Of course, if we have the set of two numbers, a and b, in this case, if we have greatest common divisor equal to 1, they will be relatively prime, and of course, they will be relatively prime in pairs. Let's give some examples. For example, we have integers 6, 10, and 15. In this case, since greatest common divisor of these three numbers is equal to 1, these numbers are relatively prime. But they are not relatively prime in pairs. But these integers 8, 13, and 21 are relatively prime in pairs because greatest common divisor of 8 and 13 is 1. Greatest common divisor of 8 and 21 is 1. And greatest common divisor of 13 and 21 is also 1. Result number 1, or theorem number 1, assume A is multiple of B. Then, in this case, we have a result that set of common divisors, of A and B coincides with the set of divisors of B. In particular, we have that greatest common divisor of A and B is equal to B. So once again, if we assume that number A is multiple of B, in this case, the set of common divisors of A and B coincides with the set of divisors of just B. This is quite obvious result. To show this, we have to, first of all, show to one side, we have to show that every common divisor of the integers A and B is also a divisor of B. This is actually obvious because A is multiple of B, and of course, every common divisor, CD, of A and B is also divisor of B. And to the opposite side, also obviously, since A is multiple of B, it follows that every divisor of B is a divisor of A. Once again, since A is multiple of B, every divisor of B is also a divisor of A. This is obvious, and that's why this number is a common divisor of B and A. So it was the proof of our result. And in particular, we will have greatest common divisor of A and B is equal to B, because A is multiple of B, and B is greatest common divisor of B. Next is theorem 2. Assume we have equality A is equal to B times Q plus C. In this case, we have a result that every common divisor of numbers A and B is also common divisor of B and C. In other words, the set of common divisors of A and B coincides with the set of common divisors of B and C. Let's write it. Let's write it as common divisors of A and B is equal to the set of common divisors of A and B is equal to the set of common divisors of B and C. This denotation is for easy understanding of this result. To prove this result, we have to show that this is actually obvious, and we will explain it without writing, just explain it. Assume we have divisor of numbers A and B. In this case, this divisor is also a divisor of C, and that's why this is a common divisor of B and C. So to this side, to one side, every common divisor of A and B, is also a common divisor of B and C. And to another side, proof is also here is obvious, and to another side, the proof is also obvious, since if we have a number that divides numbers B and C, in this case, this divisor is also divides A. And that's why this divisor divides A and B. And that's why common divisors of B and C, the set of common divisors of B and C, this set coincides with the set of common divisors of A and B. So proof is over. In particular, we have to say that greatest common divisor, or GCD, of A and B must be equal to greatest common divisor, or GCD, of B and C. This result, this theorem 2, is very important result, because it will help us to introduce an algorithm called Euclidian algorithm, how to find greatest common divisor of two numbers. This is a quite ancient algorithm, and to do this, to describe this algorithm, Euclidian algorithm. Assume we have two numbers, A and B, and we want to find this. In other words, we want to find greatest common divisor of A and B. How to do it? Using previous result, for any A and positive B, we know that we can write A as B times some integer number Q1 plus a remainder R2. And in this case, this remainder R2 is less than B, but it's not negative. So this equality is result of our previous theorems. And since here we have that this R2 is less than B, we can divide our number B by R2 and have another remainder. In other words, this B can be written as R2 times some another integer Q2 plus another remainder R3, where R3 is less than R2. but also not negative. And using this process, since R3 is less than R2, we can divide our R2 by R3, and our R2 will be multiple of R3 plus another remainder R4. And in this case, R4 will be less than R3 and also will be not negative. And using this and continuing this algorithm, we will have R n minus 2 is equal to R n minus 1 times some integer q n minus 1 plus Rn, where our remainder Rn is less than previous remainder Rn minus 1 and also is not negative. And at last we will have at some step Rn n minus 1 will be equal to Rn times Qn, and our algorithm will stop because at some point our Rn minus 1, this remainder will be 0. So we will not write this remainder, and it will be finishing point of our algorithm. Now, using previous results, previous theorem, we know that set of common divisors of A and B coincides with the set of common divisors B and R2. And the greatest common divisor of A and B coincides with greatest common divisor of B and R2. This is from our previous result. And common divisor of B and R2, or B and R2, coincides with common divisors of R2 and R3. And common divisors, or greatest common divisor of R2 and R3 coincides with greatest common divisor of R3 and R4. And continuing our algorithm, we will have that greatest common divisor of Rn minus 2 and Rn minus 1 will coincide with greatest common divisor of Rn. And it will be equal to Rn. In other words, let's write it. We can write it as or use another color. Greatest common divisor of A and B will be equal to greatest common divisor of B and R2, and it will be equal to greatest common divisor of R2 and R3, and so on. And greatest common divisor, it will be equal to greatest common divisor of Rn minus 1 and Rn, and at last it will coincide with Rn. So this Rn is the final goal. This is the number we was looking for, and this Rn is greatest common divisor of our A and B. So this algorithm gives us method how to find greatest common divisor of these two numbers A and B. And greatest common divisor of A and B is equal to Rn. And we have, once again, let's repeat results of this theorem. The set of all common divisors of integers A and B coincides with the set of all divisors of the greatest common divisor.